Welcome students. In this video we are going to learn rules for first order splitting. We know that due to spin-spin coupling between non-equivalent protons, the splitting of proton signal takes place. This is the spectra of ethanol at high resolution. When we see the spectra, the signal of methylene group and methyl group is splitted into multiplets. The signal of CH2 is splitted into 4 peaks, while CH3 group signal splitted into 3 peaks. And there are certain rules for first order splitting. And for first order spectra, the rules are as follows. First order splitting takes place due to vicinal and geminal coupling. In previous video we see what is meant by vicinal and geminal coupling. Vicinal coupling, it is a 3 bond coupling, and geminal coupling, it is a 2 bond coupling. Coupling always takes place between non-equivalent protons and it not takes place between equivalent protons. The third rule is the signal splits according to n plus 1 rule. The number of split signals n, capital N, is equal to n plus 1, where n is number of adjacent non-equivalent protons. Then next rule is the signals are symmetric near midpoint, which represents chemical shift value of protons. The area under peak is proportional to number of equivalent protons in a set. The relative intensity of multiplets is coefficient of expression r plus 1 raised to n, or relative intensity can be calculated by using Pascal's triangle. And the last rule is for first order spectra, delta nu by J is greater than 6, where delta nu is the chemical shift difference in Hertz and J is the coupling constant. These are the rules for first order splitting. Now we see these rules one by one. The first order splitting takes place due to vicinal and geminal coupling. In case of vicinal coupling, non-equivalent protons are present on adjacent carbon atoms, and the coupling between them is known as vicinal coupling. It is also known as 3J coupling. In case of geminal coupling, non-equivalent protons are present on same carbon atom. They are separated by 2 bonds. It is a 2J coupling. The coupling always takes place between non-equivalent protons. For example, in case of ethane, all the protons are equivalent protons and the coupling not takes place between equivalent protons. Another example is ethyl bromide. In case of ethyl bromide, there are 2 sets of protons, methyl group protons and methylene group protons, and as they are non-equivalent, coupling takes place between methyl and methylene group protons. That is, coupling always takes place between non-equivalent protons. The signal splits according to n plus 1 rule. The number of split signals is equal to n plus 1, where n is the number of adjacent non-equivalent protons. If non-equivalent adjacent protons n is equal to 0, then number of split signals is equal to 1. That is 0 plus 1 is equal to 1, and the nature of signal is singlet, and the unsplit signal is known as singlet. This is the structure of the signal. When non-equivalent adjacent protons is equal to 1, then number of split signals is equal to 1 plus 1, that is equal to 2, and the nature of signal is doublet. As the signal splits into 2 lines, the signal is known as a doublet, and such type of signal is seen in the spectra. When n is equal to 2, number of split signals is equal to 3. The signal splits into 3 lines. That signal is known as triplet, and that is the structure of the triplet. When n is equal to 3, then number of split signals n is equal to 4. The signal splits into 4 lines and the signal is known as quartet, and this is the structure of signal. When n is equal to 4, number of split signals is equal to 5. The signal is known as quintet and the signal splits into 5 lines. When n is equal to 5, the number of split signals is equal to 6. The signal is known as sextet and the signal splits into 6 lines. From doublet to onwards, the signals are generally known as multiplets. Only singlet, it is the unsplit signal, and from doublet to onwards, the signals are generally known as multiplets because they splits into 2 or more lines. Now consider different cases. This is the case 1. In that case, there are two non-equivalent protons, Ha and Hb. Now we see what type of signal will obtain for Ha proton. For signal Ha, n is equal to 1 because for Ha, number of non-equivalent adjacent protons is equal to 1. Therefore, the number of split signals is equal to 1 plus 1, that is equal to 2, and the signal obtained is doublet. That is, for Ha we get the doublet. Similarly, for Hb, n is equal to 1, number of non-equivalent adjacent protons is equal to 1. Therefore, it also gives doublet in the spectra. N is equal to 2, it gives doublet in the spectra. Now consider different case. In that case, there are two set of protons, Ha and Hb. For Ha, the number of adjacent non-equivalent protons is equal to 1. Therefore, number of split signals is equal to 2. N plus 1 is equal to 2. And Ha proton will give doublet in the spectra. But for Hb, number of non-equivalent adjacent protons is equal to 2. For Hb, there are two non-equivalent adjacent protons. Therefore, the number of split signals is equal to 3 and we get triplet in the spectra. For Hb we get triplet and for Ha we get the doublet in the spectra. Now consider this case. In that case, for Ha type of proton, non-equivalent adjacent protons are 2. Therefore, according to n plus 1 rule, n is equal to 3 and for Ha we get the triplet in the spectra. Now we see the signal for Hb. For Hb there are 3 non-equivalent adjacent protons. Therefore, number of split signals is equal to 4 and the signal is quartet. For Ha we get the triplet and for Hb we get the quartet. Now consider the another case. In that case there are 3 set of proton, Ha, Hb and Hc. In case of Ha, the number of non-equivalent adjacent proton is 1. On adjacent carbon atom there is only one non-equivalent adjacent proton. The Hc protons are not adjacent to Ha proton because first order splitting takes place only due to vicinal and geminal coupling, and the coupling is not possible over 5 bonds. Therefore, the coupling is only in between Ha and Hb, and for Ha, the number of non-equivalent adjacent proton is 1. Therefore, it gives doublet in the spectra. Then signal for Hb. For Hb, on one side there are two Ha type protons and on another side there are two Hc protons. Thus there are 4 adjacent non-equivalent protons. Therefore, number of split signals is equal to 5 and the signal obtained will be quintet. This is for Hb type of proton. In case of Hc type of proton, the non-equivalent adjacent proton is 1. Therefore, the number of split signal is equal to 2 and we get doublet in the spectra. Now we see some examples. This is the compound acetone, and in case of acetone there is only one set of protons. Only number of set of protons is equal to 1, and therefore methyl group proton gives singlet in the spectra. In case of ethyl bromide there are two set of protons. The number of set of protons is equal to 2, that is it gives two signals in the spectra. For methyl group protons there are two non-equivalent adjacent protons. Therefore according to n plus 1 rule, methyl group proton gives triplet, and for CH2 group proton there are three non-equivalent adjacent protons. Therefore it gives quartet in the spectra. In case of ethanol there are three set of protons. Number of set of protons is equal to 3. For methyl group proton there are two non-equivalent adjacent protons. Therefore methyl group proton gives triplet. Methylene group proton, it gives quartet in the spectra. This is because methylene group proton couples with methyl group protons, but there is no coupling between OH group proton and CH2 group proton. The coupling not takes place between CH2 and OH group proton because OH group proton is fast exchanging group proton. Therefore, the coupling not takes place between CH2 and OH, and the splitting of CH2 group proton takes place only due to coupling with methyl group protons. Therefore, CH2 group proton gives quartet in the spectra as it has three non-equivalent adjacent protons. And the OH group proton, as it not couples with adjacent proton, it gives singlet in the spectra. And remember that groups like OH, SH, NH, NH2 always gives broad singlet in the NMR spectra. These groups not couple with adjacent group protons. Then another example. In that case, number of set of protons is equal to 2. In that case, these two methyl group protons are not equivalent because chemical environment of that CH3 group proton and the chemical environment of that CH3 group proton is different. This methyl group proton is attached to carbonyl group and this methyl group proton is attached to oxygen. Therefore, these two methyl group protons are not equivalent, and in that case there is no non-equivalent adjacent proton on that carbon atom. Therefore both methyl group protons gives singlet in the spectra. For that CH3 also the number of non-equivalent adjacent proton is equal to 0. Then that example 1 chloropropane, in that case number of set of protons is equal to 3. It gives 3 signals in the spectra, and according to n plus 1 rule, CH3 group proton gives triplet, CH2 group proton gives sextet in the spectra as there are 5 non-equivalent adjacent protons, and CH2 group proton, that C type of proton, gives triplet in the spectra because it has 2 non-equivalent adjacent protons. Then next example, in that case number of set of protons is equal to 4. These two methyl group protons are equivalent as they are attached to same carbon atom. Therefore this is the A set of proton, this is B set, this is C set, and COOH group, that is D set of proton, and it gives 4 signals in the NMR spectra. Out of that CH3 group proton is attached to CH group proton and there is one non-equivalent adjacent proton. Therefore it gives doublet in the spectra. While CH group proton, there are number of non-equivalent adjacent protons. 3 plus 3, that is 6, 6 plus 2, that is 8. That is the signal of CH group proton is splitted into 9 lines. and in general it is known as multiplet. Thus for CH group proton we get the multiplet in the spectra. For CH2 group proton there is one non-equivalent adjacent proton. Therefore it gives doublet in the spectra. And for COH group it gives singlet in the spectra. These are the certain examples. Now the example, the group present on aromatic ring. In that case methyl group is present on benzene ring, that is toluene, and in that case there are two set of protons. When alkyl group is present on benzene ring, then all the protons on benzene ring are equivalent. And as there are two set of protons, methyl group proton gives singlet in the spectra. There is no hydrogen atom on this carbon atom, and phenyl group proton also gives singlet in the spectra. In that case there are four set of protons, that is phenyl group protons, methylene group protons, A type of proton, methylene group protons are B type of proton, and this is the C type of proton. These two methylene group protons are not equivalent as they have different chemical environment. And the signals obtained are, for A type of methylene group proton we get triplet in the spectra as there are two non-equivalent adjacent protons. For B type of methylene group proton it also gives triplet in the spectra as it not couples with amino group proton, it only couples with CH2 group proton, therefore it gives triplet in the spectra. And the amino group proton gives the singlet in spectra, it not couples with adjacent group proton, and the phenyl group proton gives singlet in the spectra. In that case the ortho, meta and para protons are nearly equivalent. In that case also ortho, meta, para protons are nearly equivalent, therefore it gives one signal in the NMR spectra. That is the example. In that case this is a para dichlorobenzene, and in that case all four protons on phenyl ring are equivalent. The number of set of protons is equal to 1 and it gives singlet in the PMR spectra. These are the some examples of splitting of signals. Now we see the next rule. The signals are symmetric near midpoint, which represents chemical shift value of proton. Suppose we get quartet in the spectra, then the chemical shift value of that signal, it is the midpoint of that signal, because the signals are symmetric near midpoint and that midpoint represents the chemical shift value of proton. This is the triplet and the midpoint is the chemical shift value of proton. Then the area under peak is proportional to number of equivalent protons in a set. Suppose this is the signal of 3 protons, then the area under peak is proportional to the number of protons in that set. The peak area ratio is equal to a ratio of protons in the molecule. The relative intensity of multiplets is coefficient of expression R plus 1 raised to n, where that n is the number of non-equivalent adjacent protons, or that relative intensity can be calculated by using Pascal's triangle. Look at that table. When number of non-equivalent adjacent protons is equal to 1, then number of split signals is equal to 2. That signal is known as a doublet. And for expression R plus 1 raised to 1, the expansion is R plus 1. Their coefficients are 1 and 1. Therefore, for doublet, the relative intensity is 1 to 1. When non-equivalent adjacent protons are 2, then number of split signals is equal to 3. The signal is triplet and the expansion is R plus 1 raised to 2 is R square plus 2R plus 1. That is coefficients are 1, 2 and 1. Thus for triplet the relative intensity is 1 to 2 to 1. When number of non-equivalent adjacent protons are 3, then number of split signals is equal to 4. The nature of signal is quartet, and r plus 1 raised to 3 is equal to r cube plus 3r square plus 3r plus 1. And the coefficients are 1, 3, 3 and 1. Thus, for quartet, the relative intensity is 1, 3 to 3 to 1. When n is equal to 4, then number of split signals is equal to 5 according to n plus 1 rule. The signal is known as quintet. The relation is r plus 1 raised to 4, r fourth plus 3r cube plus 6r square plus 4r plus 1. And the coefficients are 1, 4, 6, 4 and 1. Thus, for quintet, this is the relative intensity 1 to 4 to 6 to 4 to 1. The relative intensity of multiplets can be calculated by using Pascal's triangle. This is the easiest method to determine the relative intensity. This is Pascal's triangle. In that case, when there is an unsplit signal, the unsplit signal is known as singlet, and always as it is an unsplit signal, its intensity is considered as 1. When signal split into two lines, then the relative intensity is 1 to 1. When always the outermost peak has the intensity 1. And in case of doublet, there are only two peaks, therefore the intensity is 1 to 1, that is doublet. When signal split into three lines, then its relative intensity is calculated like this. The outermost are always 1 and 2 is the 1 plus 1, that is equal to 2. Again I say 1 plus 1 is equal to 2. Therefore, for triplet the relative intensity is 1 to 2 to 1. In case of triplet, the relative intensity is calculated like this. The outermost is 1. In that case, 1 plus 2 is equal to 3. 2 plus 1 is equal to 3 and outermost is 1. Therefore, relative intensity of quartet is 1 to 3 to 3 to 1. In case of quintet also, the last intensity peak is 1. Intensity of last peak is 1. Then 1 plus 3 is equal to 4. 3 plus 3 is equal to 6. 3 plus 1 is equal to 4 and outermost is 1. Therefore, for quintet, the relative intensity is 1 to 4 to 6 to 4 to 1. And for sextet also the relative intensity is 1 to 5 to 10 to 10 to 5 to 1. 4 plus 1 is equal to 5. 4 plus 6 is equal to 10. 6 plus 4 is equal to 10. 4 plus 1 is equal to 5. And that is the relative intensity of sextet. Thus, by using Pascal's triangle, we can easily calculate the relative intensity of multiplets. The next rule is, for first order spectra, delta nu by J is greater than 6, where delta nu is the chemical shift difference and J is the coupling constant. Now we see what is meant by coupling constant. The distance between two peaks within the multiplet is constant. That constant is known as coupling constant. This is a doublet and this is the quartet, and the distance between two peaks within the multiplet is known as coupling constant, and this is the chemical shift difference, that is delta nu. And when delta nu is divided by J, if it is greater than 6, or in other words we say that delta nu is 6 times greater than coupling constant, then the spectra obtained is the first order spectra. And these are the rules for first order splitting. These are the rules. Again we summarize. First order splitting takes place due to vicinal and geminal coupling. Coupling always takes place between non-equivalent protons. The signal splits according to n plus 1 rule. The signals are symmetric near midpoint, which represents chemical shift value of protons. The area under peak is proportional to number of equivalent protons in that set. The relative intensity of multiplets is coefficient of expression r plus 1 raised to n, or can be calculated by using Pascal's triangle, and for first order spectra delta nu by j is greater than 6. Thanks for watching this video. Thank you very much.